Now let's slow down and look at the real memory. We will see exactly how one doubly node sits in RAM, byte by byte. Let's zoom into one node byte by byte. On a 64-bit machine, one doubly node takes 24 bytes. This is the node holding 20 at base address 1000. This is the key memory map for this chapter. The whole block sits on the heap. This band marks it. It is one node struct, laid out from low addresses at the bottom to high addresses at the top. At the base, 1000 is the data field. It holds the value 20. The int takes 4 bytes. Next, at 1004 come 4 bytes of padding. They are empty. We need them so the pointer that follows starts on an 8-byte boundary. That is called alignment. It is the same padding rule we saw in chapter 4. On top of the padding at 1008 is the prev field. It holds 3000, the address of the node before this one. The pointer takes 8 bytes. Above that at 1016 is the next field. It holds 2000, the address of the node after this one. This pointer also takes 8 bytes. So 4 for the int, 4 of padding, 8 for prev, and 8 for next gives 24 bytes in total. Now the cost. A doubly node has a second pointer prev. That second pointer adds another 8 bytes. So each node costs 24 bytes here, instead of the 16 bytes we paid in chapter 4. Now let's look at 3 nodes together in memory. They sit at scattered heap addresses, just like in chapter 4. This time each link is shown by color, with no arrows. This is node 20. At address 1000, its data field holds the value 20. Right above it sit its 2 links. This purple row is node 20's prev. It holds 3000. That address names node 10, the node before it, so purple points backward. This pink row is node 20's next. It holds 2000. That address names node 30, the node after it, so pink points forward. The point is this. The same address in the same color names the same node in both directions. Pink is node 20's next, 2000, and that is node 30's row. Purple is node 20's prev, 3000, and that is node 10's row. And look at how far apart those addresses are. The nodes are not next to each other in memory. Only the links hold them together. Let's try a prediction first. We have the list node 10, double arrow, node 20, double arrow, node 30. We want to delete node 20. 4 link fields sit around it. Node 20's own prev and next, node 10's next, and node 30's prev. How many of these 4 must we actually rewrite to remove node 20 cleanly? Pause and guess. The answer is only 2. We rewrite just the neighbor's links. First, node 10's next now becomes 2000, so it points past node 20 straight to node 30. Second, node 30's prev now becomes 3000, so it points back to node 10. Node 20's own 2 links are never touched. We free node 20, so its fields no longer matter. And head or tail move only if the victim was the head or the tail. Node 20 is in the middle, so neither one moves. Watch out for one easy mistake. You may count 4 because there are 4 links around node 20, but only the 2 neighbor links change. The victim's own prev and next die with it. One idea from chapter 4 still holds. In pseudocode we write nil, and in C that same thing is null. A doubly list just uses it in 2 places instead of 1. At the front, head arrow prev is null because nothing comes before the head. At the back, tail arrow next is null because nothing comes after the tail. So null now marks 2 boundaries, the 2 ends of the list. The circular variant removes both of them because it wraps around instead of stopping.